Second thing that happens, we take segment number 6 out of our retransmission queue, because remember, all 3 of these duplicates have been saying, hey, where are the bytes after segment 5? Where are the bytes after segment 5? So now the guy says, okay, clearly segment 6 is the one that's gone. He says, I've been holding on to that the whole time. Now remember, all of these things here in purple, they've been counting down based on the retransmission timeout value. What is that value? Well, we don't know what that necessarily is, but this is called fast retransmission. Why? Because for segment number 6, probably the retransmission timeout hasn't expired yet, right? Remember, let me ask you this question. Do you remember what the retransmission timeout value was based on? What other timer sort of helped us to figure out what the retransmission timeout value was? It was the RTT value, right? The round trip time. Remember when the three-way handshake very first started? I sent you my sync and I started counting 1 millisecond, 2 millisecond, 3 millisecond, then wham, your sync plus ACK came back. I said, okay, let's see here. That was about 50 milliseconds from the time I sent you my sync until the time you acknowledged it. Well, that 50 milliseconds was plugged into some formula, and that came up with our smooth round trip time, okay? So that smooth round trip time then was plugged into another formula, which gave us our RTO, our retransmit timeout value. So back in like 7, 8 videos ago, we came up with an example of like 53 milliseconds for retransmission timeout. So it's quite possible that right now, when we got duplicate ACK number 3, maybe we're only, I don't know, 20 milliseconds into that. It hasn't expired yet. Well, fast retransmission says, okay, once I get that third duplicate ACK, forget about the retransmission timeout for segment 6. Don't wait for it to go all the way down to 0. Let's just queue that thing up again for retransmission. That's why we call it fast retransmission. Okay, so there it is. So now he's got segments 10, 11, 12, 13, and he's going to put segment 6 on there as well. And then one more thing happens. So the first thing that happened was we knocked the slow start threshold down quite a bit. Second thing that happened was we took the segment that clearly had been lost and re-queued it. Now notice what's happened here. Previously, the retransmission queue had segments 6, 7, 8, and 9. Why is 6 not in here? Because once we recreated it, it's not in here anymore. The only time we put a segment into the retransmission queue is after it's gone, after it's out on the wire. We don't want to start counting it down while it's still in our buffer. We haven't actually sent it yet. That wouldn't be fair. So now segment 6 is ready to go. He's got a TCP header. We're not going to start counting him as lost until he's actually out on the wire, and then we'll put him back in here. And then the third thing to happen is we take this congestion window. Remember, this congestion window had been growing and growing and growing due to the slow start algorithm. Well, now a different algorithm is in charge, the congestion algorithm, the congestion avoidance algorithm. And that says, okay, here's what I'm going to do. I'm going to resize that to 3 times the segment size plus the slow start threshold. So 3 times the segment size, if we do the math, 1460 times 3 gives us 4380. And then 4380 plus 2920. Hold on a second. This number might be wrong. Let's see here. 3 times the segment size, 1460 times 3 is 4380, plus the slow start threshold of 2920. I think this should be wrong. I think this number is wrong here. Let's just check it out. So this isn't TCP's fault. This is Keith's fault in making these slides. So 1460 times 3 is 4380 plus slow start threshold, which is 2920. Okay, no, that is right. 7,300 bytes. Okay, my notes are wrong, but the slide is right, so good. Okay, so the congestion window's basically at this point been knocked down in half. Okay, everything matches up, right? Right? Yeah. Okay, so here we are. So notice, right now, look at the comparison. Right now, the receiver is saying, hey, if you want to, you can send me up to 12 segments, up to 17,520 bytes. But our congestion window says, no, I wish I could, but because of those duplicate ACKs you sent me, we have some problems here in the network. So I'm not going to allow myself to send you that much at one time, because we got to get things sorted out here. And so now fast retransmission takes place, which is where we take segment number 6, the lost one, and everything else that's buffered, and send it out. Now remember, segment number 6 definitely has to go out. That has to be retransmitted. Anything else in the buffer, well, we might not be able to send all these, because remember, our current congestion window says we can send up to 5 segments at one time. Fortunately for us, it looks like that's exactly 5, right? 10, 11, 12, 13, and 6. That gives us 5 segments. And now he says, how many can I send right now? He says, okay, well, let's think about this. I never received, remember, the congestion window, let me just rephrase this. It's referring to how many outstanding bytes I can have. How many bytes can be out there in the world, and I haven't gotten acknowledgments yet for them. That's what this congestion window is really about. That's what we're looking at. Let me correct that error. I previously said I could send up to 5 segments. Well, yes, if I have no bytes outstanding, if nothing needs to be acknowledged, yes, I could send up to 5 segments. But that's not the case, because right now, look down here in my retransmission queue. There are bytes in flight. Remember, that was the term, bytes in flight are bytes that are out in the world that have not been acknowledged yet. So he says, okay, I never received explicit acknowledgments for segment 7, 8, or 9. However, I did receive 3 duplicate ACKs for segment 5. Those could only have been generated if the receiver received 3 segments after segment 5. My congestion window is set to 5 segments, which tells me that in addition to the 3 segments that are currently outstanding, so those are those bytes in flight, I can send 2 more. So right now, my window sent is 3 segments. My usable window is another 2. 3 plus 2 will give me the maximum of 5 that I can have. So now he says transmit. He says, okay, I can only transmit 2. So I'm going to transmit 6 and 10. And this highlighted that segments 6 and 10 are now added to the retransmission queue. That's what we see right here. So now we've got 6, 7, 8, 9, and 10. So our 5 segments, which is the maximum that we can have in flight, are gone. They're out there. The receiver acts both segments received. Now look at this. This is kind of interesting. When the receiver finally gets, he's been buffering segments 8, 9, 7, 8, and 9. Right? He's been holding on to those for a long time, saying, when is segment 6 going to show up? Well, here it is. He finally got segment 6. So we can say, okay, I'm going to create 1 ACK for segment 6 and those other 3 segments I've been holding on to forever, 7, 8, and 9. So here's 1 acknowledgement for those. And then he says, okay, for any other new segment I got that I've never seen before, which in this case was segment 10, I'll create an individual ACK for that. And so now at this point, the congestion avoidance algorithm will continue to be in control. Because remember, what was the rule? The rule was we compare the congestion window against the slow start threshold. And we said that if the congestion window was larger than the slow start threshold, then the congestion avoidance algorithm was the master. That was the one in charge of determining what's going on here. So at this point, for the rest of this conversation between these two guys, assuming nothing gets lost, the congestion avoidance algorithm will be the one in charge of now increasing the congestion window, and actually does it faster than slow start. And that'll be in charge. Now, the only reason why that would change is if for some reason a segment gets lost. And the retransmission timeout actually times out. Now you might be thinking, well, wait a second, how would that happen? Because if a segment gets lost and then I send some new ones behind it, I'm going to get those duplicates. Well, what if I don't send any new ones behind it? For example, what if I send out segment 13 and then for a while I have nothing to send? TCP connection still up, nothing to send, but segment 13 gets lost. Well, the receiver, he's not going to send me a duplicate acknowledgments, right? A duplicate acknowledgement, if I sent segment 14 after 13, let's just draw this because I don't want to get too confusing here. So let's say that segment 13 went out, then it got lost, and then segment 14 went out. Well, when the receiver received segment 14, he would say, okay, what was the last valid segment I did get? It was 12. So I'll create a duplicate ACK for 12. But let's say there's nothing else that happens at this point. Remember, the whole fast restart, if I go back to that, just to look at this. Okay, it was only when we received duplicate ACK number 3 that we actually took that lost segment out of the retransmission queue. We said, look, I'm going to stop the clock, the countdown clock. I'm just going to stop it. I'm going to take it out of the retransmission queue, send it out to you. And then we stayed in the congestion avoidance algorithm. But what I'm drawing right here is in this particular case, I'm saying if segment 11 goes, and we get an ACK for it, segment 12 goes, and it's lost. And then segment 13 goes. Well, he's not going to acknowledge 13. He's going to say, that's non-contiguous. We're missing something. So he's going to generate a duplicate ACK for 12. That was the last one he got. Now let's say some time goes by. We don't have anything else to send him for a few milliseconds or a few seconds. Very quickly, segment 12, so 11, 12, and 13 were put in here. So 6 through 9 and 10, those are gone. We received acknowledgments for those, so those are gone. Sure, we received a duplicate acknowledgement for 12, but we only received one duplicate acknowledgement for 12. If we don't receive another 2, if that's it and some time elapses, eventually the retransmission timeout value will expire for 12. Then what happens? Well, we will retransmit it, but then we'll go into slow start. Whenever the retransmission timeout value expires, forcing us to retransmit something, then slow start goes back into control. So the moral of this story is, during any given TCP connection, what controls the congestion window, how quickly it can grow or shrink, is dependent on either the slow start algorithm or the congestion avoidance algorithm. You as a human being are not going to know at any given point in time what's happening with your TCP connections, which algorithm is in control. It's all based on network conditions, the presence or lack of duplicate acknowledgments. All of that governs what's going on here.